Now let's look at the hands-on exercise for clustering algorithms. And in fact, this hands-on exercise is exactly the same as what we introduced at the beginning of the clustering session. And so basically, we are looking at a supermarket mall member profiles, and we are trying to look at the potential features or the characteristics of those customers. And then we're trying to identify the groups of different customers so that you can do the advertising or you can trying to sell the specific products to those to specific groups of customers. And again, here basically by importing the required scikit-learn package and other Python packages for numerical analysis as well as visualization. And then we're going to go get the data for the more customers. And this is basically trying to showing a couple of examples of what we are seeing. So basically you are looking at those potential features, gender, age, and the annual income and spending. And then the first algorithm we are going to test is the k-means clustering algorithm. And the reason actually we need to talk about this hands-on exercise is because we mentioned that for k-means clustering and Gaussian mixture models, you have to predefine this so-called hyperparameter k. But often in practice, you don't know what's actually a good k to use. In this specific hands-on exercise, we are going to introduce two model selection methods for k-means clustering or for Gaussian mixture models. You can do essentially the same thing. So the first method is known as the elbow method. So elbow method is essentially trying to look within cluster sum of squares, so within cluster distances again, and then you basically use whatever number of clusters you want to use and to check within cluster distance performances. You plot it out, the curve, the performance with respect to k, the number of clusters you use. And then the elbow decision rule is to identify the joint or the knee or the elbow joint in the plot, which means that across that specific k, then within cluster sum of squares or within cluster distance is going to decrease very little. So after that point, then you're going to say that you don't want to increase the number of clusters anymore. So to be specific, actually, this is the code implementing what we just talked about. So this n clusters is a possible number of possible k's that you can use. And for each of k's, you do the k-means clustering, and then you compute within a cluster distance or within cluster sum squares, or you compute the silhouette score. And then if you are using the elbow method, then basically you are going to plot this within cluster sum of square versus k, the number of clusters you're using. So if for k from 2, 3, 4, 5, within cluster sum of squares is still increasing reasonably fast, but after cluster 6, you can see that the decrease of the within cluster distance or within cluster sum of square is minor. So you are trying to decide whether this is the elbow point. If you think about this is a forearm, then this is the elbow joint. Or if this is a low leg, then this is a knee joint. So you're going to say k equal to 6 maybe is reasonable k to use for this k-means clustering algorithm. So that's the elbows method. And then silhouette method, basically you're just looking at the silhouette score as we introduced as the last clustering performance evaluation metric. And notice that neither of the elbow method or silhouette score-based method requires the underlying cluster assignment, because in fact, in this hands-on exercise, we don't know the ground truth partition of the customers. So if you plot the silhouette score, then in fact, k equal to 6 achieves the highest silhouette score, as we explained. Now, if we fix k equal to 5 or 6, then what we can do is to visualize what's going on. So indeed, if we do that, then we can see on the clustering assignment, if you look at the income and the spending, then you can see it seems that there are intuitively 5 clusters here. But if you look at edge and the spending score, then maybe the clustering is not that clear. And in fact, you can also trying to visualize the clustering assignments in 3-dimensional space, which may give you a better idea how you are clustering this customer data point. So you can check on the Python code how to do that. So this is basically the k-means clustering, and you can do the same thing for the Gaussian mixture models. So essentially, you just use the scikit-learn Gaussian mixture model package and do the assignment. And if you want to look at the clustering visualization results, it's something like this. Again, the trains are similar, and you can also do the cut and paste Python code to visualize the results in the three-dimensional space. And then you can also test your dbScan clustering algorithm. And for dbScan clustering algorithm, if you remember when we talk about that, there are two hyperparameters we need to choose. One is a minimum number of core samples you want to have. And also, how do you consider the samples as core samples with respect to the current data point, epsilon, the distance threshold? Basically, this is another kind of model selection. So we are going to change the epsilon values. We are going to change the minimum number of core samples requirement values. And then based on the dbScan algorithmic procedure, this heat map tells you, based on different samples, how many clusters dbScan actually identify. So you can see that if you only allow 3 to be the minimum number of required core samples, then definitely you are seeing more clusters. And also, if you look at a small neighborhood to identify core samples, then you also get the relatively large number of clusters. So the neighborhood size increasing the number of required core samples in the neighborhood, then you get the trend that decreases the number of clusters. But for this specific customer example, you can see that in many regions for dbScan, you are getting either 5 or 6 clusters. So here, and then what do you can also draw the heat map based on the different hyperparameter settings for epsilon and the minimum of required core samples. You can compute the silhouette score, and then in fact, if you check the silhouette score, this one 0.26 seems to be the highest silhouette score in this grid search. And then if you look at this silhouette score, it's indeed corresponding to number corresponding to 6 clusters in the final results. All right, and also you can attest to your hierarchical clustering algorithm on the same data set. So you can also attest to your hierarchical clustering algorithm building scikit-learn to this customer example. And essentially, if you look at the arguments here, so we again are trying to find the cutoff threshold to achieve 5 clusters. And when we are trying to iteratively merge clusters, we are using a word linkage method. So word linkage essentially is trying to make sure the variance after you merge the cluster, it's relatively small. And based on that, you can get the clustering results or your customer data set. And again, you can do the same visualization to see the same trend that indeed this customer clustering is highly dependent on the spending as well as annual income. And again, you can visualize using dendrogram visualization. So that's all about clustering for unsupervised learning. Thanks.